Hi guys, it's Mrs. Webb here. I just wanted to take a little time today to introduce position time graphs to you guys so that we can start looking at them when we get into class together. So this is just going to be the first part of the position time velocity time graphs that are in the D2L notes. So I'm going to break those notes into two parts and we're going to look at them over the course of 2 days coming up here. So today really what I want to introduce you to is the idea of a position time graph and what it is that we can learn from reading the graph in terms of, what is the information that it gives us, what is the data that we can collect, what is that particular slope of the line telling us. Okay, so we chatted a little bit last time about position and what that indicates. And so what position is that term position? When you see a position time graph, what that tells you is the location of that particular object. Kind of like the coordinate systems. If you were looking at a grid system on a map or something like that, that would be the position of that particular object. And in a position time graph, what we're looking at is what is the position of the object over time. So we're manipulating the time axis and we are seeing how the position responds to that manipulation. Right. And so we spent a lot of time last week talking about graphing and all of that. So I'm sure that part of it is pretty straight in your minds by now. I also introduced the term uniform motion to you guys last week. And when we talk about uniform motion in physics, we talk about an object that is moving at a constant rate. So I used the example of an object or a car, for example, that is on cruise control. And it's moving at a constant rate of 50 kilometers per hour down the street, right? So we know there's no acceleration up or down of the car, right? It's just on cruise the entire time. And we're going to focus right now, just to start, we're going to focus on uniform motion graphs. And then once we've got a handle and we've got our minds wrapped around the position time graphs, for the uniform motion scenario, then we'll introduce the uniform accelerated motion where objects can speed up or slow down. So the thing to note, there's a couple of things. We chatted a lot about finding slope last week. When you look at a position time graph, if you have a positive slope, what that positive slope is telling you is that what it's telling you is the direction of motion. So if you've got a positive slope, you're moving toward that positive direction. And that positive direction, remember that in physics we assign the positive to a specific direction, be it forward, backward, left, right, north, east, southwest, right? We assign the positive to it. So if we have a line that has a positive slope, that's going to indicate to us what direction that particular object is moving. Very much like when we did our calculations and we ended up with a number that had a positive magnitude to it. If it has a negative slope, well, that also tells us that it's moving in the negative direction. Okay, much like the calculations told us last week. Only difference here is that instead of doing calculations, we're reading that from our graph. So I've got an example of a graph here. Oh, and before I do move forward, if we have a horizontal line on our graph or the slope is equal to 0, well, in that case, what that tells us about the position is that particular object is going nowhere. It's not changing its position over time. It's staying in one spot over time. So if we look at this graph right now, first thing we want to figure out is we want to orient ourselves, kind of like if we were looking at a map. We want to orient ourselves so that we know exactly what this graph is telling us. Our time is on the x-axis, so it's being manipulated. And most importantly, I suppose, would be what the y-axis is, because this is going to tell us what it is we're plotting, which is really important when we start looking at velocity time graphs and acceleration time graphs. But more specifically, it also tells us what direction is that positive and that negative. So in this case, we're plotting displacement, and it's telling us that we're measuring it in meters north. So what this tells me right now is that anything that is on the positive side of the y-axis, that's going to indicate movement in the north direction, or a position in the north direction. Anything that is located here on that negative side of the axis tells me that there's a position located on the south, right? And the zero is that point where we go from north to south. Now, if we go back to our slopes that we were talking about up above, in this case here, we have a horizontal line. And so what that's telling me right at this point is that from 0 to 2 seconds, this object is going nowhere. So it's at 10 meters north, and it continues at 10 meters north until 2 seconds. And if we look, all of a sudden at 2 seconds, there's a change. All of a sudden, that object starts moving from 10 meters to 15 meters to 20 meters to 25 meters to 30 meters between 2 and 3 seconds. So between 2 and 3 seconds, this object has displaced itself a total of 20 meters to the north. Its position at the 3-second mark is at 30 meters north. That's where it's located. But its displacement has displaced itself from its starting point 20 meters in the north direction. Now, for another second here, the object remains steady. It doesn't go anywhere. And then all of a sudden, we see a change again. The object starts to move from 30 meters north, and it starts to travel back. It moves from 30 meters north to 20 meters to 10 meters to 0, right? It goes to that, that reference point. And then all of a sudden, it starts moving south. -10, -20. Towards the south. Okay. So that's kind of how we would look at this axis here. Now, a couple of things that we can figure out here is you can obviously see that in this segment here between 2 and 3 seconds, and then between 4 and 6 seconds, you can see that we have a slope that's associated with that particular line. So what we want to figure out is, what does this slope tell us? Because remember that when we initially introduced the concept of graphing in physics, we said that that line, the equation of the line, a lot of times will give us an important formula that we use in physics. The slope will give us an important variable. Areas under the line will give us important concept as well. And so if we look, our slope is our rise over our run. Well, what are the units for our rise? Our rise are meters over our run, which is seconds. So think about that for a second. If your slope is meters over seconds or meters per second, what variable is this position time graph slope giving us? Right? What do we measure meters per second in? Well, meters per second give us the variable of velocity. So our slope in a position time graph gives us our velocity of the object. So if we were to calculate the slope between 2 to 3 seconds, that tells us that we finish here, our V2, or our D2, sorry, is our 30 meters. Our D initial is is 10 meters. Our 30 minus 10, D2 minus D1, over time 2 minus time 1, that's going to give us 20 meters over 1 second. So that tells us that in this particular 1 second period, the object is moving at a constant velocity of positive 20 meters per second. And what that positive sign indicates is that it's 20 meters per second north. Right, so it's moving in the north direction at 20 meters per second. Now, if we calculate the slope over here, what you have is your initial point. That's where the start is. And we finish down here. And so I'm going to calculate this for you. Or let me just check if I have got it down here. I'll calculate for you over here on the side. Oh, that's kind of thick. So we've got slope is rise over run. And that's our displacement final minus our displacement initial over our time final minus our time initial. And our displacement final is at negative 20 meters. Our displacement initial is at positive 30. And our time final is 6.0 seconds, and our time initial is 4.0 seconds. So this tells us that we move at negative 25 meters per second. And what that negative sign is telling us is that this object is moving at 25 meters per second in the south direction. That's what the speed of the object is. Between 4 to 6 seconds. That's what my speed is, my velocity, sorry. Okay. So what we can do is we can figure out what is our velocity from 0 to 2 seconds. And if we run our slope calculation, I mean, it's pretty obvious, it's a horizontal line. So in this case, the object is stopped at 10 meters per second. So our velocity is 0 there. The object's not moving. From 2 to 3 seconds, we figured out that the object travels north at 20 meters per second. From 3 to 4 seconds, the object is stopped at 30 meters north. And then from 4 to 6 seconds, the object is traveling at a constant velocity at a speed, oh, I did have it down here, of minus 25 or 25 meters per second south. Okay, that's if I wanted to figure out the velocities over specific times. Now, the other thing I can do is I can figure out, and I haven't done this for you, but we're going to do it because we're going to practice it in class. The other thing I can do is I can ask, well, what is the average? We figured out the average velocities over specific time increments. What about if I was to ask you, what is the average velocity over the entire trip, right? And you have to remember that average velocity is our total displacement divided by the total time it takes for us to cover that displacement. And so here, I'm going to move over here to the side. And this is for 0 to 6 seconds for the entire trip. And that's my rise, which is my displacement, over my run, which is my time. Because we're looking at a graph, we're going to look at displacement final minus displacement initial over time final minus time initial. And we're going to figure out what is the, let me put this in here, what is the slope? I'm going to use a line here. What is the slope from here to here? Okay, what that is the average for the entire trip. So when we were calculating last week, right, we would have taken our displacement 1 plus our displacement 2 plus our displacement 3 plus our displacement 4 and divided by the entire time. On the graph, because we have a graph available to us, we can look at what is that displacement initial and what is that displacement final, and we can take the slope for that line in order to figure out the average speed or velocity for that entire trip. So our displacement final And I know it's final because my object starts here, so that's the initial, and this is my final because that's where the object stops. And my final happens at negative 20 meters per second. Negative 20 meters, sorry. And my initial was at positive 10 meters. My final time is at 6.0 seconds, and my initial time is at 0.0 seconds. And that tells me that over the course of the trip, this object has been traveling at negative 1.6 repeating meters per second, which tells me that the average velocity for this object over the entire trip was 1.6 meters per second to the south. Right? That's the same thing you guys would have figured out doing your velocity calculations, your average velocity calculations last week. The only thing now is that we're figuring this out in terms of our graphs and reading the graphs and knowing that the slope of the line on a position time graph tells us what the velocity is of the particular object. Okay, so I'm going to leave that here for today. We're going to do a bunch of practice with this slope and figuring out position and locations and all that kind of stuff, speeds, all of that, when we see each other in class. So if you guys have questions, let me know. And then tomorrow what we're going to do is we're going to look at being able to go from this position or this position time graph to a velocity time graph. Okay, so I hope you guys are doing well. Let me know if there's any questions, and for now, take care. We'll chat soon.